Hey everybody. Today we're talking about z-scores in the standard normal distribution. The standard normal is just the normal distribution with mean 0 and standard deviation 1. So the PDF is a bell curve and its peak is at 0 and its points of inflection are at plus and minus 1. Really important fact about the standard normal. If you have a random variable x with any normal distribution, say mean mu and standard deviation sigma, then x minus mu over sigma has a standard normal distribution. And we typically denote such a random variable with the letter z. The proof of that fact uses an important technique that comes up a lot when you're working with continuous random variables, so I want to wave my hands at it really quickly. Whenever we're trying to understand a continuous random variable, like z in this case, we tend to look at the CDF, the cumulative distribution function, the probability that z is less than or equal to any specified value little z. We can write that probability statement in terms of x, that's what you're seeing me do on the top line, first just substituting z for what it's equal to, x minus mu over sigma, and then solving that inequality for x. Then we unpack that probability statement using the CDF for x itself, so writing that definite integral that you're seeing on the middle line. Finally, we do a change of variables and out pops the CDF of the standard normal distribution, n of 0, 1. For any particular x value, we call the corresponding z value, x minus mu over sigma, the z-score, or standard score of the value x. The z-score represents the number of standard deviations by which x lies above or below the mean. The probability that a randomly selected z-score lies in a certain range is the area under the graph of n of 0, 1 over that range. So for instance, on this slide, I'm picturing the probability that z is between -1 and 0.5. In other words, that if we get a z-score just at random, we're looking at the probability that it's between -1 and 0.5. It's represented by the area under this curve that is shaded, the fraction of the area that's shaded. As with any continuous random variable, the total area under a density curve, including that of n of 0, 1, is 1. We compute standard normal probabilities using the cumulative distribution function, or CDF. And so this is the case for the standard normal, as for just about any probability distribution for a continuous random variable. I've illustrated it here. We're looking at the area to the left of a specified value z. That's the CDF. It's typically denoted with this capital phi of z. So for instance, this picture shows phi of 0.5, the probability that z is less than or equal to 0.5, the proportion of the area under this graph that is shaded to the left of 0.5. Visually, we can estimate that about 70% of the shaded area, or rather 70% of the area under this graph is shaded. So phi of 0.5 is about 70%. Now, most statistics books these days still include a table of values for the standard normal distribution, but the calculations are definitely best done using technology. I use R, where the standard normal CDF is represented by the p-norm function. So for instance, to do that probability that we looked at on that last slide, we're going to enter p-norm of 0.5. And when we do that, we get 0.6914625. So that estimate of 70% wasn't too far off. Here's another example. You can try this on your own before seeing my solution. Find the probability that z is between -2 and 0. So we're trying to get the shaded area here, the shaded area under this graph between z equals -2 and z equals 0. The way we're going to do this is by taking the area to the left of 0, that is the CDF of the standard normal evaluated at 0, and then subtract off the area to the left of z equals -2. So we're going to evaluate the CDF of the standard normal distribution at -2. Using R, we're doing p-norm of 0 minus p-norm of -2. That comes out to be about 47.7%. Any normal probability calculation can be done using the standard normal distribution instead. If x has a normal distribution, then the probability that x is less than or equal to some specified x value is equal to the probability that z is less than or equal to the corresponding z-score. So basically just translate your x values to z-scores and then do your probability calculation there. For instance, in a recent year, scores on the SAT were approximately normally distributed with mean 1060 and standard deviation 195. Using z-scores, find the probability that a random SAT taker scores between 900 and 1000. So what we're going to do here is we're going to translate each of those two values of interest, 900 and 1000, into z-scores, just using that z-score formula, x minus mu over sigma. In these two cases, we get z-scores of negative 0.821 and negative 0.303 respectively, indicating that each of these two values are a little bit below the average performance on this exam. We then compute the probability that x is between 900 and 1000 by doing p-norm of negative 0.303, negative 0.303 being the z-score corresponding to x equals 1000, minus p-norm of negative 0.821, negative 0.821 being the z-score corresponding to x equals 900. When we do that, we get about 17.5%. That's the probability that a randomly selected test taker has a score in this range. That value is going to be exactly the same probability that we'll get if we do the calculation directly using the normal distribution with mean 1060 and standard deviation of 195. You can see the R code for that as well on the bottom line here. Visually, this means that the two areas that we're seeing in these two plots are exactly the same. On the right, we have the region between negative 0.821 and negative 0.303 in the standard normal distribution. On the left, the region between 900 and 1000 in the normal distribution with mean 1060 and standard deviation 195. Two more useful facts to keep in mind as we wrap up this video. First of all, since the probability of any particular z value is infinitesimal, the probability that z is less than or equal to z and the probability that z is less than z are the same. Basically, you don't have to worry about whether your inequalities are strict or not when you're inside of a probability statement for a continuous random variable like the standard normal distribution. Secondly, the standard normal is symmetric about 0. So the probability that z is greater than some value is the same as the probability that z is less than the negative of that value.